Okay, so the second experiment is another assay type titration as well, but this is done on iron 2 sulfate or ferrous sulfate. Okay, the titration will be done against potassium permanganate. Okay, potassium permanganate. So this experiment is divided into two parts. Okay, the first one would be the standardization of the potassium permanganate solution. So this KMnO4 is a very strong oxidizing agent, and they don't come straight away in the solution form. Okay, they normally come in solid, and you have to dissolve it to turn into liquid. And this particular titration, the concentration that you are going to prepare is 0.1 N normality, or which is the same as 0.1 M, okay, molarity. So you have to prepare 0.1 M KMnO4. But what is the purpose of standardization is that you want to make sure that the potassium permanganate solution that you have prepared is actually 0.1 M, meaning that the concentration is exactly as stated, or it could be less, but we want to know the exact concentration. If let's say it is 0.099, or maybe it is more than 0.1 or 0.12, for example, so that later on when you titrate it against the sample, which is the iron 2 sulfate or ferrous sulfate, the calculation later on the formula, you will use the correct concentration. Okay, and for this standardization of the potassium permanganate solution, it has to be done against oxalic acid. Okay, if you still remember in the lecture, okay, on the volumetric analysis on the primary standard, one of the example primary standard is oxalic acid. It is suitable to be used as a standard in which you want to standardize any solution, because oxalic acid is very how to say stable. Okay, so if it is you prepare at 0.1, it will still give you the exact amount 0.1. So these are the uh, reaction, okay, of the manganate ion. It will be converted from MnO4 minus to Mn2 plus. So basically the number of oxidation number will decrease. Okay, from the left side, I think this is Mn 7 plus, okay, to 2 plus. So this one, okay, so the principle is quite long, okay, but it basically tells you on the reaction itself. So iron sulfate or ferrous 2 sulfates is one type of iron compound, okay, mainly used as a formulation to treat iron deficiency, okay, for people with anemia, and also sometimes prescribed to pregnant ladies. Okay, to sometimes for pregnant women, they lack red blood cells. So to increase that, doctors may prescribe iron compound as well. Okay, so this iron becomes part of the hemoglobin and myoglobin, because in our red blood cell, that's why our blood is red color, because the of the iron 3 plus. Okay, so the assay of the ferrous sulfate is based on the redox titration, in which your iron 2 plus will be converted to iron 3 plus. So from iron 2 plus to iron 3 plus, it will undergo oxidation, while for the manganese, it will undergo reduction. Okay, so the number of oxidation number will decrease. So here the limit of ferrous sulfate, meaning the reading that should be obtained, the result should not be less than 98% and not more than 100.5%. So this is the values that you should get for the experiment. But doesn't mean that if you get less than this, your experiment is wrong, meaning that the sample itself does not meet the expected values. Okay, so the procedures are divided into two steps. So the first one is the standardization of the potassium permanganate itself. Then only you can proceed with the assay. Okay, so the standardization is done against oxalic acid. So here are all of the procedures to prepare. First, you have to prepare the oxalic acid solution first, in which that 10 ml. Uh, you have to mix it together with dilute sulfuric acid. Okay, and then you have to warm the solution up to maybe around 50 to 60 degrees Celsius. Okay, some other references that I have found, they heat the solution up to 75 degrees Celsius. So it depends on the references that you are using. And then you can titrate it with 0.1 N of the potassium permanganate until the pale pink color is obtained. And for these two titration, there is no external indicator is added, because this is an example of internal indicator in which that your potassium permanganate itself will be the indicator. Okay, because the color of the potassium permanganate solution will normally be dark violet. Okay, and the color changes that you want to observe is normally pale pink. Okay, so once you get that pale pink color, it has to be repeated until you get 3 concordant values. Okay, then only you can do the calculation. So you have to do the calculation in order to make sure what is the concentration of potassium permanganate. So number 5 here is more like a precaution for the titration. So keep the solution hot during the titration, meaning that the solution that is in the conical flask. So you can do it on top of the hot plate, but another option is uh, you have the hot plate ready, okay, on one side. So take it, put the beaker, the conical flask on the hot plate, then you can do the titration, but once in a while you have to reheat again to make sure that the temperature is between 50 to 60 degrees Celsius. So if let's say a brown precipitate is formed during the titration, okay, it can be results from the temperature are low temperature, meaning it is too cold, or the addition of a manganate solution is added too rapidly, meaning you add the titrant from the burette too fast, or the amount of sulfuric acid to dissolve the oxalic acid is insufficient. So this could be any one of these reasons. So once you obtain the concentration of the potassium permanganate, then only you can go to the assay of iron sulfate. So the calculation, we jump to the calculation first. Okay, so this is the standardization of 0.1 m Kmn04, whatever the concordant value that you get. So that can be calculated first. Okay, maybe you get 0.1, maybe you get 0.099. So once you have confirmed the concentration of the potassium permanganate solution, then only you can proceed with the what you call uh, the assay. Okay, so the assay is quite straightforward, like in the first experiment, the assay of sodium bicarbonate. So you just prepare your sample, Here, only 1 gram of the sample is needed, and it has to be diluted with sulfuric acid. Okay, dilute sulfuric acid to dissolve. Then you can straight away titrate with 0.1 m potassium permanganate. Okay, and the color changes should be faint pink, so very very pale pink color. So this one, okay, you have to make sure that you get 3 concordant values as well. So the each ml of the potassium permanganate solution used is equivalent to 0.0278 gram of iron 2 sulfate. So these values will later be used uh, in this where is it? In this uh, formula. Okay, so but first, this is the calculation for the uh, potassium permanganate. So once you get this, then you can use in this formula. So this equivalent weight factor EQWTF, the value is what is stated in the procedure, which is 0.0278. So there are some for this experiment. There are some questions as well. Okay, so you can answer it together. Then okay, let's see some of the videos that I've put. Okay, there are 4 videos over here. Okay, the first videos, this one I want you to watch later, but this is 40 minutes. So I'm going to show the other videos. This is shorter. So, but the first videos is a very good example because it will it shows the step meticulously from standardization up until to the titration part. Okay, so I hope you watch the first videos later, but I'm going to show you this one reaction of the potassium permanganate under the acidic condition, just to show you on the reaction itself. Okay, I'm going to jump straight to the experimental part. So that is the observation or the reaction part. It's not actually a titration, but as you can see, once the iron sulfate solution is added into the potassium permanganate, okay, the color from like violet or purple color change or turn into colorless. But during the titration, the potassium permanganate solution that will be added into your sample or the iron 2 sulfate, and we will normally stop when the color turn to like pale pink. Okay, pale pink. Like this. Another one. Where is?
Standardization of potassium permanganate. The reagents required are a 0.02 molar KMnO4 solution for this titration. Dissolve 3.16 grams KMnO4 in 1 liter. A 0.1 molar ferrous ammonium sulphate solution, which can be obtained by dissolving 3.92 grams in 100 milliliter of the solution. Add 10 milliliters of 0.5 molar sulfuric acid to this solution. And lastly, you will need 0.5 molar sulfuric acid solution. Pipette out 10 ml of the ferrous iron solution into an Erlenmeyer flask. Add 10 ml of 0.5 molar sulfuric acid to this solution. Fill the burette with the potassium permanganate solution. This is a reaction on which the lab is based. After pipetting 10 ml of the ferrous iron solution into an Erlenmeyer flask, add about 10 milliliters of 0.5 molar sulfuric acid. Now add potassium permanganate from the burette. Use a stir station to constantly mix the solution. At the end point, you will observe a persistent pale pink color to the iron solution. That would indicate the end point of the titration. Now the titration is complete. Using the volumes of potassium permanganate and the iron solution, you can now calculate the molarity of the potassium permanganate solution.
Okay, so another will be this one.
This lab will go over the guidelines of our very first redox titration. Usually we associate titration just with acid-base reactions. And often we are utilizing and indicate to signify when we've reached the stoichiometric. Not with this lab. This lab involves a reducing and oxidizing agent that in and of themselves will color change to signify the equivalence point, stoichiometric point for us. Some safety precautions first. Potassium permanganate is a beautiful. It gives the appearance of a gray compound. However, when placed in water, it shows itself as a very deep violet colored solution. That compound, potassium permanganate, reacts with anything organic to create a deep brownish kind of compound. So we want to make sure we're wearing gloves to just protect skin. We want to wear aprons to protect our clothing. And we want to make sure that we are fully rinsing any equipment that came into contact with potassium permanganate, because upon sitting it will stain. In fact, our reagent bottles that'll hold our potassium permanganate solution look dirty, but they're just stained. So they're clean, but they're stained. So you want to be careful about any paper that comes into contact with. We need to make sure we are being very cognizant of fully rinsing our burette after the potassium permanganate has been introduced, because any plastic portions will become stained if tiny residues left behind. We are also acidifying the iron solution, so we want to be extra careful. We're using 3 molar sulfuric acid and then 85% phosphoric, which you know is weak acid, but it's a high concentration. We just want to be cautious in it. So you're going to follow your instructions, and you'll need to first follow the math that's given, and we are going to make ourselves a potassium permanganate solution. You're simply adding the solid to the bottle and then adding almost, up to where the portion or the bottle begins to narrow, be about 500 milliliters. And we're going to standardize this, so it's okay if we're a little bit greater in our solvent addition or lesser. Now, be careful too, because we know that we want to agitate to help speed solution formation, but you have to be careful if you have any leaks. So if you want to get some paper towel, just be extra cautious, because we of course should overturn this to make sure we've created a homogeneous solution. Whenever you're at rewashing, please make sure that you pass the potassium permanganate solution through, of course, the spout. So I encourage you to have just a waste beaker to catch overflow. Now I definitely encourage you, if you feel more comfortable, to utilize a funnel. Go ahead and pour in any excess potassium permanganate solution, but you can of course loosen this at any time to add more. You want to be extra cautious that you are reading this on eye level, and you do not read it until you pass it to the make sure you have a constant column. You need to talk with your lab partner because this is so deep in color. It's tricky to read the volume up. So talk with your lab partner and make a decision. Is it easiest to measure the very top where the liquid meets the side of the mirror? Now we know we read the bottom of the viscous, but with this deep colored liquid, that may be easiest. Or you can see reflection and definitely read the bottom of the viscous. Decide with your partner, and of course you can ask me for guidance. Because with this titration, we are after the difference in volume. As long as you are consistent with how you read, either always from the top or always from the bottom, always from the will deliver fine results. Don't worry about needing to start at a certain volume. You can always add. You want to start when it's at eye level. Again, you're going to follow the directions. You will create 3 samples of an acidified FAS solution. Now, our reactant ions in this lab are the aqueous permanganate, the aqueous 2+ plus 2 ion. The source of the permanganate is the potassium permanganate, but potassium is the spectator. The source of the iron plus 2 is FAS. That's the nickname given. And you'll understand why. The name or the formula is actually iron 2 ammonium sulphate hexahydrate. Woo! Quite a mouthful. So FAS for short. All the others are spectators. This delivers the iron 2 plus reactant. We are going to acidify the environment. So you're going to follow the directions. You're going to add a certain amount of iron. Make sure we're doing difference by mass. I would go ahead with Sharpie and identify which is 1, 2, and 3. So you can keep track of them. But feel free. We don't have to use an Erlenmeyer. You can use a beaker. Now I would instruct because we're probably going once we've added water, acid amount. You're not going to have a ton of analyte volume. So we want to make sure that it's deep enough that you could definitely signify color change. So if you want to use the Erlenmeyer to prevent splashing and loss of liquid, I encourage you to do that. But you can use a beaker as well. And you can also use a stir plate if you'd like. So remember, stir plate, we want to go ahead and carefully add our magnet, make sure it's placed centrally, and then when we turn on our stir, just get a nice gentle agitation. All right, so we have our 3 acidified iron samples. We know, because we made them, given the mass of the FAS, we can then convert to get the moles of the iron plus 2 that's in each of our samples. Get the balanced reaction. Know how to create a balanced redox reaction. Remember, we're in an acidic environment. Then what you will do is make sure that you are noting the initial volume. And then very carefully and patiently, especially with the first trial, we are going to titrate until the reaction shows us that we've added enough permanganate to react all the iron plus 2. So how will we know that? Well, the permanganate is the deep purple compound. Now, iron compounds are usually a mustard or a deep kind of pumpkin orange color. However, the other ions that are there gives FAS and the hydrate this a very mild green color. However, whenever you put it in water and then your acids, the concentration that we're making will definitely look clear. We'll be adding this very, very intense purple liquid to a clear liquid. Purple, clear. Your products. This is unbalanced. Your products are a clear ion and a clear ion, and maybe some water, clear. Maybe you're consuming hydrogen ion or producing hydrogen ion, clear. So you're taking something very intensely purple, clear, and getting clear product. So while there is iron present, iron plus 2, to react this, you will get clear. And as soon as this has been reacted away, then the unreacted permanganate ion will give the purple color. So you will titrate, slowing down the purple color, keep staying around, and then stop when you have very, very light violet. That violet should remain. It could lessen in color after about 60 seconds. So as long as you have that just gorgeous, just the palest purple. Now sometimes the iron ion can be a little finicky and kind of show you a yellowish at times. But push through that, you're looking for the palest purple, which because we're adding purple, if it goes a little yellow, it could at times look peach, but you are looking for that pale purple. I will demonstrate that in just a moment, a little closer, so that you can see, what kind of purple we're after. So, our first exercise, you know the mass of FAS, you can then get the moles of iron plus 2. You will know the volume of potassium permanganate. You will have balanced and gotten the correct mole ratio of these ions. Then you can determine to the level of sig that you're permitted per the instrumentation, the concentration of your potassium permanganate. Then part 2, you're going to obtain 25 milliliter samples of your unknown. 3 trials. It's already acidified. You will start with that. You now know the concentration of this. So we know the volume, the concentration. That allows us to calculate the moles. You have the balanced ion ratio of your reaction. But now we're looking for the concentration of the iron plus 2 or 2 plus here. So that is our exercise. Be very careful handling the potassium permanganate. This is a great adventure. I will challenge you to get the palest purple possible. Be really patient with the first trial and have the first trial inform your second and your third for both steps of this experiment, because that gives you kind of an idea of the volume that your trial 2 and trial 3 of both parts will require. Best of luck, stay safe, enjoy this chemistry.
Okay, so this is a very good explanation basically on the experiment, and she talks a lot about the precaution that you need to take care during doing the experiment. Okay, like when you want to prepare the potassium permanganate solution, okay, the way you put the potassium permanganate into the burette, okay, you need to wash the burette, like I said earlier. In fact, she said to wash it at least 3 times, okay, and the eye level when you want to take the reading. So when you are doing titration, it's not just trying to get the titer value or the volume of the titration itself. Okay, it's more on the precaution measures, okay, in order to always get the most accurate result for the analysis. And this one also, there is a screen experiment in which that you can try. Wait, I share with you. So for this one, same step. Okay, just press quick start and select titration level 4. Okay, this would be a titration or assay for iron to detect the amount of iron in tablets, okay, using potassium permanganate solution. So this is basically almost the same experiment that that you are supposed to do. The only difference is that the sample itself are in tablet form, okay, in formulation form. So just as the previous screen experiment, you just follow the step, okay, watch some of the videos. This is iron in
The Food
dietary.
Standards Agency are testing a batch of iron supplement tablets to check that the amount of iron in each tablet is correctly stated on the bottle. The amount of iron, or more specifically Fe2 plus ions in each tablet, can be determined by performing a titration experiment with potassium permanganate. This is called a redox titration because both a reduction and an oxidation reaction occur simultaneously. Redox reactions involve the transfer of electrons from one species to another. A useful way of remembering the flow of electrons is to use the oil rig acronym. This reminds us that the oxidized species loses electrons and the reduced species gains electrons. When we add potassium permanganate to the iron solution, the Fe2 plus ions are oxidized by the permanganate ions and lose electrons to go from a 2 plus to a 3 plus oxidation state. At the same time, the permanganate ions are reduced by the Fe2 plus ions and gain electrons. Here, the manganese is initially in the 7 plus oxidation state and is reduced to the 2 plus oxidation state. There is no need for the addition of an indicator in this titration because the presence of the permanganate ions will turn the solution pink when there are no more Fe2 plus ions to react with. This is the end point of the redox titration. As an analytical chemist working for the Food Standards Agency, you will perform a redox titration experiment to confirm the exact iron content in the iron supplement tablets. You will then check that the value is in agreement with the amount listed on the product label.
Okay, so basically it is almost the same, in which that the titration involve titrating iron 2 plus ion against the manganate, okay, but in this screen experiment, that iron is available in the tablet form. So you just follow the step and so on, okay, until the end of the activity of the screen experiment. I think there are, about 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 steps, okay, until you are supposed to finish with this. Okay. So for this experiment, okay, I mean for the report part, I did not give you the raw data as in the first experiment, but what I want you to do is to sort of come up with the titration reading so that the percentage purity that you obtain will be 98.5%. Okay, so this is sort of like back calculation. So like the first one, the assay of sodium bicarbonate, I already gave you the title reading. So you can calculate from here to obtain the percentage purity. But now I already gave you the percentage purity, so you can came out with any values, okay, for the titration, as long as it gives you the same value of 98.5%. Okay, just by using the same calculation method that is in the manual. So that is all for experiment number 2. So any question?